Hello everyone, this is Yun from WPI. I will present our work, Understanding Hyperbolic Metric Learning through Hard Negative Sampling. Recently, there are a lot of works have been proposed to learn the representations in the latent space, so that the learned representations could be further used for downstream tasks. The common idea of this representation learning is that we want to put the representations of the similar image in the latent space as close as possible, while pushing away the different representations from the different images as far away as possible. The loss that is commonly used by contrastive learning is the info-NCE loss. Recently, there are works that not only learn the representation in the Euclidean space, but trying to explore the representations in the hyperbolic space. Hyperbolic space is a homogeneous space with a constant negative curvature. The distance between points in this space is decided by the negative curvature. From the origin to the boundary of the space, the distance between points are getting larger and larger. The motivation of this work is that we found for the same anchor point, different geometry representations might find different negatives, and they are complementary to each other. So we want to learn a representation that can cover different geometries. In this image, we show that the x-axis is the tau value in the info-NCE loss, and the y-axis is the accuracy. SPH here is a spherical, means we learn the representation in the Euclidean space, and the HYP is the representation learning in the hyperbolic space, and the C value here is the curvature value we can change for the hyperbolic space. Previous work found that if we learn a representation in the hyperbolic space, it will get the superior performance comparing with the Euclidean space. However, we found that if we can select the correct tau value during the learning, no matter it's in the hyperbolic space or in the Euclidean space, we can always get the comparable performance. It's just that we need to select a different tau value in the different geometry representations. So we further analyzed the gradient of the info-NCE, and we found that there is an important value px minus that is related to the triplets, means the anchor point, the positive and the negative itself, together to determine the importance of the negative during the learning. We show that for the different negatives in the same batch, when we sort them according to the distance between the negative itself and the anchor point, different geometry will select or assign different scores, different px minus score to these negatives. That will determine the whether these values or these instance representations should be considered as the hard negatives during the learning. For the detailed analysis, please refer our paper. We also proposed a mixed geometry learning. The idea is that only learn the representation in the single geometry is not enough, because we have different geometries that can select different negatives. This is kind of like providing the negative pool, and by combining them together, we find the really meaningful or useful negatives or hard negatives for the same anchor point. We show that when we combine the different geometries, we could learn even better representations comparing with a single geometry learning. Thank you.